situations to identify what is possible and to generate data to learn models of the world and sensory motor skills. This is mainly the fundamental difference with continual learning approaches, where the robot does nothing else than start solving a task from the very first moment it is turned on. Many different challenges have to be faced when trying to apply machine learning models on real robots in an open-ended learning setting. Some combine deep hierarchical reinforcement learning and continual learning mechanisms, but the introduced dream architecture is the first one, to the best of our knowledge, that implements most of them, tests relevant approaches, and describes how to connect and articulate them in real robots. The dream architecture additionally considers the building of discrete representations from low-level sensory motor values, building new action representation, state representation learning, passing by symbolic representation, and skill discovery. Starting from a reward that defines a task and policies to observe at least some rewards, the SRL module generates a task-specific state space. This approach relies on raw perceptions. The design of a state space can be seen as chicken and egg problem, as the policy is required to generate observations to be used later, and in order to generate also a new and relevant state space that can be used for learning policies. We tackle this problem here with random policies and a simple button pushing task, but more complex policies could also be generated to bootstrap the generation of state spaces. Although most of the continual learning approaches works are building learning processes that can deal with the continuous flow of data and the different tasks with a single learning process, Dream decomposes the learning into different processes. Some in charge of bootstrapping the representational redescription process, some acquiring skills and consolidating them to make them more robust, etc. Being endowed with a transfer between short-term and long-term memory, the DREAM approach includes an instance of dual memory learning system. After the DREAM project concluded, we have been recently studying explainable AI as a key dimension of our vehicle towards never-ending learning. But why explainability is pursued? There are different purposes of explainability that are sought by different audience profiles. The reasons to demand explainable models lie in different roles concerned with verifying fair decisions for users, certifying models' compliance with legislation, audits, ensuring new functionality, or simply understanding as domain experts. But what is explainable AI? If we consider the classical definition of Guidotti et al., we thought a relevant dimension was missing in order to properly evaluate explainability. So part of our contribution was putting audience as the key aspect to be considered when explaining a model. So giving an audience an explainable AI is one that produces details or reasons to make its functioning clear or easy to understand. We will use a model as the target of our explainability, considered here to illustrate the different levels of transparency. But we could also have examples, data set, an output class. So simulatability is the ability to simulate strictly by a human. The composability is the ability to explain each input, parameter, or calculation without additional tools. And algorithmic transparency is the ability to understand the process to produce any output where the model has to be fully explorable by mathematical analysis and other mathematical methods. So why is explainable AI actually important for reinforcement learning? With the rapid development of RL, the needs for explanations of RL algorithms and ethical AI systems becomes critical. It's also a requirement for the EU guidelines of ethical and trustworthy AI. And we see some categories refined here from our larger XI taxonomy, where, for instance, the model can be tweaked to learn simultaneously both policy and explanation. This way, explanations become a learned component of the model, and there are other categories. You can see more in the survey. So on the right, we see an action influence model, for instance, based on a graph that explains a specific action for a star StarCraft 2 agent, we can obtain content factual explanations. For instance, asking the question, why not building a barrack? Indeed, the explanation provided by the graph in bold arrows says, because it's more desirable to do the action build supply depot, since the goal is to have more destroyed units on destroyed buildings. Here is another example of how a trained agent to solve Atari and how it's explained with an explainable AI post hoc method. Saliency maps here can be used to determine what part of an image observation is used by the actor and by the critic. In red, we have the saliency for the critic, in blue for the actor. And the comparison shows the differences among bits, Jacobian saliency and perturbation-based approaches in an actor-critic model. Now, can we use Shapley values, for instance, to explain the contribution of each agent in a cooperative multi-agent environment? We have been studying this, and this is the same formula as for the original Shapley value formulation, but instead of feature, we can consider agents. And instead of model prediction, we can use the global reward, so the sum of rewards of all the agents in the considered team. So we have to make M rollouts of the game with different random coalitions to estimate the Shap value of one player with and without him. Now, explainable AI can provide answers to some of these questions. Can a Shapley value be used to determine how much each agent contributes to the global reward? Or is every agent contributing positively to the common goal? Are they behaving sustainably? What training episodes, key features in observation, or agent actions are actually decisive in the learning? Okay, so another idea we worked on recently is exploiting explainability in order to penalize the model for not mimicking the reasons an expert will use as an explanation of the model. We propose the ex-nihil methodology for explainable neurosymbolic learning to fuse deep learning representations with domain expert knowledge graphs. This methodology includes three main ingredients. First, a deep representation learning component, then a symbolic knowledge representation component, here knowledge graphs, and an explainable AI-guided learning procedure that we term here Shap backprop training that enforces the alignment of both. With two datasets, we show that the better classification performance, the more explainable the model becomes, and the learned representation allows to remove noisy information. Now, can we add human interventions in the loop that help during learning? The question we pose here, should artificial agents ask for help when in a human-robot collaborative problem-solving setting? We take as base an empirical study in a human-robot interaction setting, which investigates children problem solving from a developmental perspective. And the main hypothesis is that child-robot interaction, problem solving, it's a setting where children that voluntarily interact with the robot are more likely to show better performance and improvements over time than children that interact in a turn-taken setting. Charisi et al. Actually considered this game of Tower of Hanoi and conducted a behavioral experiment to evaluate task performance and designed two types of robot interventions, voluntary and turn-taking. The conclusion of this article that interests us is that the exploration is important in young children problem solving, and that children develop actually inhibitory strategies that emerge and develop in patterns over time. Starting from this conclusion and considering that it would be valuable to transfer developmental discoveries to AI, we try to verify if this hypothesis is also true in a simple reinforcement learning algorithm. We want to check if when solving a simple closed-ended task, receiving help from an expert accelerates the learning of this task depending on whether the intervention is canonical or requested by the agent. In other words, whether the learning is driven by the teacher or by the learner. In this case, we consider the game towards of a node, and our agent learns a simple Q-learning algorithm. And to be as faithful as possible with the behavioral study design, we change two parameters, the canonical intervention rate and the ask for help threshold. Mainly, if the best policy value is lower than the ask for help threshold, the expert will play instead of the learning agent. Here are our results for the two scenarios where we measure success based on the number of moves to resolve the game. Where we see that the learning agent is directly more efficient when it's helped by the expert in a turn-taking scenario. However, it's even more effective when it's helped every 4 turns rather than every 2 turns, showing that it's important for the agent to be able to explore on its own rather than having always the optimal solution. The asking for help agent is also quickly more effective since it does not know yet what to do, but after asking for help many times during the first episode, it starts solving the task by itself, resulting in an increase of inefficient moves. We interpret this as the learning agent gaining confidence in movements, which even if not perfect, it still allows the task to progress towards its resolution through different trials and state explorations. We believe, however, the addition of a mechanism such as intrinsic motivation on the desire for the learning agent to solve the game by itself could increase the accuracy of this comparison. Our learning agent asks for help when it considers that a movement is not good enough to be played, whereas in reality, this mechanism pushing the child to actually ask for help are much more complex. So this is one of the main possibilities for future work to expand on. As future work, we need to explain, we're seeing that recent studies demonstrate that attention is actually not necessarily explanation, and thus we need to be in better position to explain the latest deep learning architectures, reinforcement learning architectures, and the intricacies of this. Also, to better explain the failure modes of explainable AI methods and why and when agents will benefit from human help. Thank you for your attention. Happy to hear your questions.
Thank you, Natalia. Let's see if we have a question. Yeah, bottom. Yeah, you can now open your mic and talk.
Hi, very nice presentation, Natalia. I'm really glad that I was able to participate in this conference and hear your presentation.
Hello, everyone. Thank you for inviting me. I am Natalia Diaz Rodriguez.
Sorry.
Yeah, no worries. So I have like the main question I have is how do you deal with this kind of explainability for very large models? Like, are some models too complicated to explain? And I'm thinking now of like AI models that have millions of parameters, like I don't know, deep convolutional neural networks, for instance. And then the second question would be, if we are talking about explainability, then what is really the trade-off between explainability of performance?
Yeah, this is a very good question. Let's say it's the holy grail that we are all trying to solve, how to maintain performance and efficiency while not compromising explainability, right? So we see that in our latest work of ex-Nesil neurosymbolic architecture, more, for instance, when we have to detect an architectural style, we take a picture of a facade and we want to say this is Muslim style because it has this Arabic art and this other column of this type. So of course, the more accurate the detector is, the more a grade will be your classifier, but we also see that not always the more performant your overall model, your overall classifier is, it's not always the more explainable. So this is shown to be the case in some cases, in others no, and with real quality of the data, it's very important. Like you really need to make sure that you have signal to pick up and proper annotations that refer to the actual concepts you need to distinguish. So the data quality becomes evident that it's really very important to make sure that it's not unbiased and it's representative of your data, of your problem. And indeed, the more complex your model is, it's harder to track. And there is plenty of work to do still, because as we are seeing, the heat maps sometimes respond to things that we developers want to see. So as long as they seem satisfying for us, we see what we want to see, we are happy with it. But this might not be always the case, or in every case, the explanation we expect. And also this can be hijacked or, suffer counterfactual attacks, for instance, adversarial attacks, sorry. And so it's very important to have counterfactual explanations. That's what I wanted to say. What would have been different to not predict this output, or that is this the same as the expert will agree with, or what we will agree with. So there's plenty of components, and I think the more we account for, the more we are verifying our network, because we need to certify them somehow, and they will be put in production. So definitely a lot of work to do still.
Thank you. And we have one question in Q&A, and probably this will be our last question we're taking before the lunch break. Katarina is asking, I am new to explainable AI. How are you representing knowledge graph information in deep learning as matrices of ones for each relationships?
Yeah, so in this case, we are simplifying a lot the knowledge graph. We just look at hierarchical relationships, like the object, what we call compositional model. So a whole is composed by the part, a whole object, like let's say a dog has a tail, 4 legs and 2 ears and 1 nose. This is the level that we model in our work so far, but we can also model other things, like the family of the animal. Is it living on earth, in the sea, other things, of course. So far we have done it very simply, just having a knowledge graph that is not directly ingested by the neural network, but instead, because we know this is a simplification of what the expert agrees, like Romanic art has this kind of arc, this kind of door, this kind of column. So this is rather simple, and it's not needed to feed it. What we do is just that we correct in the traditional gradient descent through back propagation. We say, okay, if the model, what is the model giving importance to, which attribute, and if this attribute is not aligned with the one that the expert believes is the responsible for that style, then we penalize the model. So it's a bit more like correcting or regularizing the model you could think of in the error, rather than representing and feeding this as a bias. But that's very interesting too, and I think we want to study further graph neural networks and how this would merge the knowledge together from the very beginning. This is always a trade-off of biasing your model or correcting it. And but of course, we think that if there is expert knowledge result from many years, why shouldn't we use it, right? So this is a bit our thinking. So yeah, a lot of exciting approaches to try. Thank you.
Thank you very much, Natalia, and thank you all for attending the morning session. Now we are going to have a lunch break for 1 hour, and we get back here at 1 o'clock. See you all then.
Thank you.
Thank you. Hi, Alison. Do you want to share the screen, to test sharing the screen to make sure everything is fine?
Hello there. Yes, I can.
Hi. Yeah.
Here we go.
Yeah.
Yeah. Do you want me to
Yeah,
leave? Shall I leave
No,
it on?
Yeah, you can. That's perfect. Yes. Thank you.
Notice I made it on time.
Yeah. On the right time.
Despite my, yes, I'm so bad with time zones. Thank you for the reminder.
No problem.
Okay, I'll mute myself.
So I think we'll wait a couple more minutes because it was a lunch break and people are just joining in again. Okay, let's begin. Welcome back to Women in Data Science Turku event. I hope you have had a relaxing lunch break and have had already a cup of coffee, so you're ready for our next speaker that I'm very excited to introduce. Professor Alison Happenstall is a professor of geocomputation at the University of Leeds and also an ESRC Turing Fellow. She has particular interest in data analytics, developing approaches for detecting hidden spatial temporal patterns in big data, quantifying uncertainty in simulations, and building more robust individual-based models through probabilistic programming and reinforcement learning. We already heard about smart building in the morning. Let's go bigger scale, see how smart cities are. Floor is yours, Alison.
Thank you so much. Can I just check? I am off mute, aren't I?
You are, yeah.
Thank you so much for the invitation. I mean, the talks I've seen so far are brilliant. So it's really exciting to be amongst women who are doing this type of work. My talk is going to be a little bit more general. I want to give you a flavour for agent-based models and the sort of systems that I'm working within. And I do work within social systems, spatial social systems, and a lot of my work falls within urban analytics, and hence the cities. So I'm going to give you a bit of a flavour about that and examples of the work we're doing. But I'm probably also going to complain quite a lot because of all the problems and the challenges that we have in this field. Feel free to throw any questions at me. Right. Okay. First off, acknowledgements, mainly because I always forget to do this. I work with a great team of people at Leeds, which need to be flagged. Andrew Crooks in the States as well. And there's a lovely book there if anyone's interested in learning more about agent-based models. Okay, so we were supposed to meet in person last year. Sadly, some things happened that we can't. So I thought I would say hello from where I am. I am at the University of Leeds, and Leeds is in the north of England, in the county of Yorkshire, which is a beautiful, beautiful place. There's a bit of scenery. The picture of the people in the red jackets is my brass band where I play. But Yorkshire is famous for our Yorkshire puddings. We like our pints of beer and our cups of tea. So I would love for any of you to come and visit us in Leeds. We have a huge amount of agent-based modelers, and we'd be really excited to have anybody come to visit us at the moment. So back to the talk. As I said, I'm going to give you a flavour of what is the problem that we're particularly interested in dealing with. What is an agent-based modelling, and hopefully why are we using an agent-based model? Some examples of how agent-based models have been used, just to give you an idea of it. And then, as I said, some of the challenges that we have and work that's ongoing. And it's really great to see the previous talk on reinforcement learning was absolutely fantastic. And I'll be talking a little bit about reinforcement learning as well. So there's obviously lots of crossovers going on. Okay, so first of all, this video was taken in a bygone era where we could walk around freely. This is Trafalgar Square in London. And this is one of the biggest sort of tourist attractions there is. Now, there are people there. This was taken, I think it was about 1 o'clock on an afternoon. Who are these people? What are they doing? Where are they going to go? We don't know. This is sort of known as the ambient population people who are moving around cities in the daytime, and we don't really know what they're doing. We have lots of data that can try and help us. We have environmental data. We will have footfall counters, traffic cameras, air pollution counters. And we'll also have social media devices, phones, people check into places. Now, if we can link those data sets together, we can start to answer, who are they? What are they doing? Where are they going? And that would be incredibly useful for urban planners, councils, and so forth. We also have all this sort of new data, and we have machine learning methods as well coming online. Some of these machine learning methods have been around for decades, have just been rebranded, but we have a lot of new methods that are coming online to help us deal with this data. Now, one of the big problems we have with this data, one of the many problems we have, challenges, are understanding, fusing the data together first to make it a wholesome data set that's verified, but also interrogating it to understand what patterns are emerging that are important that we need to put into our models. Now, if we can take the machine learning and the data, bring them together in some way, we can start to answer some really complicated questions. So what would the impact on the health service in the UK be if we pedestrianised the centre of London? Therefore, no cars, no air pollution. What would air pollution do? How would that impact on how people move around? How would that impact on their health in both of exposure to air pollution and obesity? So these are really complicated questions that we can't answer at the moment, but we have all the raw materials there. And that's kind of our motivation in the urban analytics and agent-based modeling. We want to be able to use data and methods to understand cities, to make them better for people to live in. You know, this kind of is the same thing. Why are urban environments so difficult to predict? Well, in an answer, space, geographical space. There are no hard, fast laws in geography. I know there's one there, I'll come to that, as opposed to physics, maths, chemistry. Social systems there is no universal law of social systems. Space is particularly a headache because what may happen at one point in time and space can be completely different to another time. A process at your very first day of your simulation could be really important and completely unimportant at the end of it, and vice versa. Space is really difficult. Understanding how trends and processes emerge over time and space and how they feed together is incredibly difficult to get on. We have allegedly one law, Tobler's law. I'm not convinced that this is fully rigorous anymore. Everything is related to everything else. Near things are more related than far things. You could probably argue that that still does work. Human behavior, I'll come back to, but some aspects of human behavior are very hard to simulate. Now, with my classes of students, I would at this point ask them to pick a number between 1 and 4. And I could guarantee at least 80% will pick the number 3. Now, that tells me that there are some aspects of human behavior that are easy to simulate and model in. Pre-COVID times, most people would leave the house, go to work, come back in the evening, perhaps some diversions. There's some routine behaviors that we can simulate. However, there's lots of other behaviors, softer behaviors that are really hard to understand. And again, this is where data may help us. There's been a huge shift, certainly in the spatial social sciences, from modeling populations as a whole, the aggregate level, purely because we had no data or enough computational power to do anything else. But a lot of work in the last 50 years has been based on aggregate level work. Now, with data and computational models, we now realize that individuals are really the drivers of social systems. They power the processes. Mike Batty said cities are products of individuals, networks. These networks that have flows of information, money, disease lately, that sort of thing. So we really need to be looking at understanding, simulating cities from the bottom up, not the top down. Which brings me nicely to agent-based modeling. I don't know if anyone knows what agent-based modeling is, so this is my lecture slide that I tend to use. SimCity, this is a computer game that was popular probably a couple of decades ago, is a great example. On the bottom right, you have an avatar. You create one of these in your agent-based model. You give them attributes, usually from a census. You give them behaviors. You create a virtual environment. You put them in there and let them wander around and interact. You see what emerges. Emergence being one of the key elements of agent-based models. You don't know what you're going to get out of it from what you put in. I'm going to really show my age here. The little clip thing in the middle, that's Mr. Clippy. He was the original Microsoft Word help. And he's been cited as the very first agent. And you'd be doing something in Word and he'd pop up with some annoying advice in a really sort of peppy manner. Universally hated. And the guy who actually coded him had death threats and went into hiding. But probably showing my age a bit there. How have agent-based models been used? Well, this slide was put together a couple of years ago. Of course, if I did this in the last 12 months, all we'd see is COVID, dreadful COVID models. But prior to COVID, there's quite a spread of applications of how agent-based modeling has been used. Now, on the axis down in your bottom left, it's minutes and sort of micro models like neighborhoods, buildings, going all the way up to migration. Now, probably 95% of applications would fall within up to the day line. A lot of the agent-based models are very small scales, time scale. Now, the reasons for that are data and computational work as well. If you construct a really detailed agent-based model and you have agents interacting, feedback, etc., it's still, even with cloud computing, massively computationally demanding. I just wanted to give you a flavor of a type of work that's out there. Now, as I keep saying, data is been one of the sort of, I think, transformational elements, along with the increase in computational power, that's really brought agent-based modeling along. Having all this data is fantastic. As I said, previous 50 years, we've had very little data, built big aggregate models, spatial interaction models, we've moved people along. Now we're actually have the opposite problem. We have too much data, absolute potential of what we could do, but there's a massive problem is that we don't know quite what to do with it or how to handle it. So there's huge amounts of work going on in data wrangling, so taking all this data, fusing it together to make really usable data sets. And that's going to be fantastic for agent-based modeling in helping us address validation, behavior, et cetera, which I will come on to. I put this one in because I just wanted to drive home a point that these sort of new data, these big data, really help us get on behaviors. And if we can grab that behavior and we have all this data at an individual level, we can start building models that allow us to explore different scenarios. So if a tube strike happens, a train strike in one of the UK cities, what will happen? A big drive at the moment in the UK is looking at, once we're eventually let out of lockdown, how can we alter the urban infrastructure to have people move around in a more safe manner? Should we pedestrianise roads, put in new street furniture? That's a huge one. These models can really help us do that if we know how people are going to move and behave. The little screenshot is just to amuse myself, really. This we had our UK Prime Minister. We developed a track and trace app for COVID, and the UK Prime Minister was like, this is going to be world-beating, brilliant. It really was, because it was so dreadful. However, the idea of it, people going around with this app, collecting data, knowing who they've interacted with and where they've been at what time, it kind of represents a holy grail of sort of data sets that certainly in my area we'd like to get hold of. Obviously, for reasons of ethics, we wouldn't be allowed that type of data, but it's a tantalizing thought. Okay, I'm going to give you a couple of examples of where we've gone wrong and some good work as well. So this is work, one of my colleagues, and the idea here was, okay, we've got these agent-based models. We want to understand how people are moving around a town, well, a city ultimately, but let's start with a town. Can we take all the different types of data sets, create this agent-based model? Can we calibrate and validate it? Really important, can we validate it so we know what we're seeing actually is going on? So the UK census was used to create a population. Lots of other different types of data sources were used. UK time work survey, which a lot of people fill in, so we know roughly where people are doing and what they're doing during the daytime. We put people into houses and we watched them go off around. I don't know if I can get this. I don't think you'll be able to see it, but the blue dots will move around as people move around. And we calibrated this against sensor data. So all these, this is a couple of towns near where I live, near Leeds. And the councils all put sensors in because they wanted to know how many people are in the town centre. Is it related to tourism? So we had access to this data. So we had a great data source to be able to calibrate against as well. What could possibly go wrong? Well, let me tell you what went wrong. So the dark line is the real data. That's actually what happened. Our first attempt is the dotted line. So you can see around about 10 o'clock, there's a massive difference between the model prediction and what actually happened. But we've got all the right data. We've built a really good model. We've done sensitivity analysis. Why, oh why? Well, so I went and presented the results of this to one of the science cafes at one of the towns. And a very strong message came back to me. Yes, your model's all lovely in that, but you've forgotten a really important demographic here. So in all of the models that we built, we hadn't captured the retired population. Now, normally in the UK at 10 o'clock in the morning, the adult working population have left to go to Leeds, Bradford, one of the nearby cities. The children are all in school. So the people who we hadn't captured moving around these towns were the retired population, the grey population. So we went and found other types of data that captured this, put it in, and then the result was much better. I think this is really important as a lesson for data-driven modelling is a great idea in theory, well, but you still need to talk to people, and you need to embrace the sort of theories as well around the areas. We had lots of data, we did all the testing and that, but we still were way off. We hadn't uncovered the right processes, and that's really key to these models. Behavior is another headache. You'll get the impression that agent-based modelling is one long headache, and you are right, but it's fun headache. Behavior is really hard to do. As I said, all this new data we're getting is fantastic because it's given us an insight into a potential insight into what people are doing and why they're doing it as well. And this has kind of spawned a whole area of behavioural agent-based modelling. So now if you go and look at the literature, there's huge amounts of behavioural frameworks out there that you literally can just drag and drop into your model, thereabouts. The example I've got here is some work that we did a few years ago looking at criminal behaviour. And this was inspired by work we worked with the local police force, and they wanted to understand if we're going to redevelop an area of Leeds, what's going to happen to some of the crime. In this case, it's house burglary, people breaking in and robbing your house. We had data from the police, we had all sorts of statistics, but we also had interviews with burglars. I must point out, these are the unsuccessful ones, the ones who have been caught and in jail, but we had that information as well. What motivated you? So we developed a model, a virtual environment of Leeds, and we had virtual burglars. And we had this agents can also be buildings. So our agents were buildings, and they're also individuals. The individual burglars, we used a model called PECS, physical, emotional, cognitive, social, 4 different areas that would control the behavior of the burglar. So if they were hungry, they would go eat. If they were tired, they would sleep. If they wanted money, they would look for opportunities to burgle, to get goods to sell. Which, you know, it still is crude, but trust me, at the time was quite a sophisticated way to do this. So here, and again, this is a little age, you're going to see red dots moving around, and these are burglars. The underlying image, this is Leeds. This is an area of Leeds called Headingley, quite close to university, and it's one of the most burgled parts of the UK because every street has big houses with 6 students in with lots of laptops and other things burglars would find attractive. Sorry, I've just lost my mouse key. There we go. So you'll see little red stars moving around. Those are the burglars going about their business, and it will zoom in. At some point, you'll just see them go into a house or a building and they burgle. Then they move on. And then, but all this behavior is driven by this behavioral model. Great. So what we did then, as I said, there was a big regeneration project ongoing in Leeds at the time. So we used this model, simulated the part of Leeds that was going to be redeveloped. The houses would be much more secure. And the police wanted to know where would the crime displace. And we predicted really well where crimes would move within the area. And what's nice about this work is that it was a behavioral model. We had lots of different types of data in there as well, but we had huge amounts of engagement with the police as well. And they really fed into the process of developing the model and took the results to develop into their strategy for target hardening, making the area safer from burglars. So that's kind of a nice successful example. This example, I could not bring myself to put anything COVID in. This is an example from Andrew Crooks. And actually, I think it's, even though it's almost 10 years old, is still a really nice example of how you can use agent-based models, other types of data and behavior. He looked at the spread of cholera in a refugee camp in Kenya, Somalia. Gathered all sorts of crowdsourced data, made the model so explicitly the agents will make a decision about where they're going on need. So not quite as sophisticated as the previous example, but within that direction. And there's all these different factors that they took into account as well. So a kind of sophisticated model. Knowledge was fairly universal in this model. So if an outbreak of cholera happened in one place, everybody knew about it, which is kind of a limitation, but still. They put in a very simple SEIR model. We've probably all heard about these models in the last year, but that was embedded in, and it related to the environment as well and to decision making. Results of this, you know, what was nice is that they sort of predicted the outbreaks in there, which matched fairly well with what had happened. But they also played around with a bunch of different types of interventions. Okay, so on day 6, if we do this, what happens? What it doesn't do, there was no social networks in there. As I said, knowledge was universal. So if there was an outbreak of cholera in one place, everybody knew and avoided that point. Which is probably fairly unrealistic. So social networks would be really useful to have in there as well. There's also no real-time updating. So the model was initialized on day 0 and it ran. So if something major happened around day 9, this model couldn't take account of it as well. And probably these types of models, you want to be fairly reactive in what they can do. Which takes me to the elephant in the room. So yes, so we've had this little COVID thing going on. I think in terms of my area, it has been a curse and a blessing. Certainly within my research group and with Maturing, the work that we were doing was essentially put on hold, and we've been focused on doing different types of work to do with COVID. Why is COVID a curse and blessing for agent-based modelling? Well, this article appeared here in the Washington Post last March, and it is a really good article. They use NetLogo, little simulations to show how a simple agent-based, individual-based model can model disease spreading. And I think this caught a lot of people's imaginations. Now, agent-based models, you can construct them really easily. There's so many packages out there now where with minimal coding experience, you can just go and type and produce a model. That's the downside of it. In the UK also, I should add that our eventual lockdown last March in the UK was informed by an individual-based model out of Imperial College. So that, along with these sort of articles, really sort of put individual-based modelling right at the forefront. The result being that when you go to Google Scholar, type in the word agent and COVID, you just get masses of articles. The curse of this is that majority of these articles are poorly initialized, poorly validated, and whoever has written them, they don't really understand agent-based modeling and what it can do and the limitations. So really bad science. And I guess the upside is that this is helping promote agent-based modeling to be more accepted and understood as a technique as well. But yeah. There's a rant there, but I don't have time for that one. This I found, which I thought was interesting. So I'll set the video up in a moment. This is from about 2014, and it's from an article in Nature. And somebody took an agent-based modeling and thought, what would happen if there's a global pandemic? And in this case, a flu pandemic. So what you'll see, I'll set this off. Here we go. So what you're going to see in a moment are some blobs, red blobs appearing. People are coming into the West Coast of America with flu. How do these people spread across America? And you'll suddenly see these blobs where the major airports are in urban centers. And then, annihilation. No, everyone's ill. Everybody recovers. It's a happy ending. But this is a really nice example of agent-based model and space, and it operates a very simple disease transmission model at the back of it, but it's also huge. 250 million people I think were simulated within this, so a really nice example of what we could do as well. Right, sorry, I lost my mouse. So why am I've been talking about bits and pieces? Well, certainly within my area, within Maturing in the UK, there is a massive drive towards real-time simulation, the creation of something called digital twins. Now, digital twins in this context are the sort of SimCity simulation or within a computer. And you can see why it's an attractive prospect. If you can simulate all the different interventions, you can play around with things in your computer. And agent-based models are sort of being touted as the technique to drive all of this. Now, as I said, there is a number of challenges. I've got a theory about a law, Heppenstall's law, that once a technique of some sort, these big navel-gazing articles about the key challenges, future developments, issues start appearing, the technique has reached some point of acceptance, and that is absolutely the case with agent-based modelling. Prior to the deluge of COVID articles in the last 12 months, the literature is saturated with all these big articles. I'm guilty of them myself. However, interestingly, there was an article back in 2008 by Andrew Crooks. It's a really great article, and it listed out these are the challenges we need to meet. If you read any of the articles that have come out in the last 2 years, those challenges are still there. For some reason, we have not really advanced very much on the methodological challenges. In terms of applications, we can simulate absolutely everything, but we're not sort of tackling the behavior, validation, calibration, understanding the complex results that we have in there. I'm going to run out of time, so I'm not going to go on too much. So the last few slides are just sort of quickly work that we're currently doing in Leeds to try and address some of these challenges. And there is great work going on at other institutions as well. One of the things we're looking at is data assimilation, real-time data assimilation. Can we put data into a model as it's running and for really accurate short-term predictions? So if an incident happens in our city and we need to know what people can do within like the hour, that sort of time scale, how can we do that? Data's coming in, can we throw it in and have live predictions? And why would we want to do that? Well, really, we probably know, anyone who does modeling know that you start your model and your output at day one match. As you go along, they diverge, you put new data in, and you converge back. But we want to keep them as close together as possible. We're doing that by playing around with a bunch of techniques, Kalman filters, etc. And we've got it's a really simple example, but we started with a train station. Can we simulate how people move from one side of a train station to another? We have data on this. Can we input data in real time and get it right? Very, very simple start. It turns out that, you know, putting data into your model in real time is a lot more complicated than we anticipated. Something else that we're doing is uncertainty quantification. So other disciplines do this so much better. This is virtually absent in agent-based modeling. Maths, meteorology in particular, have fantastic, well-developed methods. Now, of course, the systems they apply it to are very different to the sort of social systems, nonlinear systems that we have. However, there's a lot of potential for adaptation. So we've been playing around with history matching, ABC, which is used a little bit. The idea being that, can we shrink down the solution space to get the right sort of parameters in our model to match what we need at the other end? And can we use these to sort of quantify the uncertainty as well? Please contact me about this afterwards. I'm not going into details now. This one I almost took out because Natalia's presentation I thought was fantastic, but we're also sort of dipping our toes into reinforcement learning. And this time, you know, with the problems I've talked about with behavior, if we use reinforcement learning, can we put our agents in a city, a 3D environment using Unity? Can we get them to learn the behaviors we want? One of the big problems, I guess, in most models is you tend to initialize based on historical data, things that have happened in the past, not what's going to happen in the future. And that could be a limited range of behaviors. And you might need a much broader behavior. So can we get the agents to learn behaviors themselves? It's sort of things we're playing with. I put these videos in just a simple illustration I stole from my colleague Ed Manley of what a trained agent looks like. It goes between two goalposts, and what an untrained one does. But I think the previous presentation has told us that. Okay, to summarize, so I'm working in urban analytics, simulating cities using, amongst other things, agent-based models. Cities are predicted to grow to, well, the number of people who live in cities will be greater than those who don't by 2050. Massive inward migration. There's a real pressure to understand how cities function now, so in the future we can make them more sustainable, more equitable, we can make them really work for the people who live in them. Things like global pandemics and, you know, that's a major shock to a system. How can we use this sort of modelling system to release people from lockdown, make the cities safer, understand how people move around? There's massive amounts of challenges going on in spatial agent-based modelling. Space is a real pain. You know, if it's just time, great, but adding that complication of space really does give you a new set of challenges. And how to meet those challenges really is by looking at what other people do in other disciplines, you know, what are the advances in physics, maths, psychology, and bringing those in to agent-based modelling as well. Being collaborative, agent-based modelers tend to sit in their own little ivory towers and not share. And maybe that's because our application areas are so unique that I wouldn't have much to share with somebody who's an ecologist agent-based modeler, but there needs to be greater collaboration. Data is an ongoing issue. But you know, there's lots of really promising work going on to develop the agent-based modelling. Just please don't build COVID models anymore. And that's all I have to say. Thank you very much.
Thank you very much, Alison. Like always, it was very fascinating to listen to you. I totally enjoyed it. So let's see if there is any question. I already have something in the Q&A, and one of the attendees is asking if you could provide a reference to the Colorado disease transmission model paper.
Oh, the Colorado, yes, it's Andrew Crooks. I think it's Crooks 2014. If you just Google that. Andrew Crooks has got a really good website. He's at Buffalo State University.
Yeah. And I saw Aina had a question. I opened, you can talk now.
Can you hear me right now?
Yeah.
Can you hear me right? All right, thanks. So I actually have two questions. First of all, thanks a lot for the very interesting presentation. So I remember you mentioning that you do some calibration of the data against sensors. Can you specify, do you use Kalman filters or something else for that?
Yeah, so in that work, so the Kalman filters are used for data assimilation type work, which I can send you some reference to, or you could email me offline, we can have a quick chat. That other work that I presented with the sensors, it literally was just, we were doing counts, mean counts against it, so nothing too sophisticated. But the other work with the Kalman filters, I'd be really happy to have a chat with you about. It sounds like you might know something about it.
And then I had another question, which is, so you were talking about these limitations, especially in context of COVID, when you use this agent-based modeling. So what would you say are then the main limitations?
The main limitations, data understanding, poorly defined models. I reviewed a bunch of COVID models for one of the journals I'm an editor on, and the models, the assumptions are so gross that nothing meaningful will come out at the end of them. There's no engagement with epidemiologists or really, understanding the transmission rates in there. Poor data to build in behavior. No data to real data to actually validate the findings. It's kind of like, yes, this is how a transmission model would work, but the whole research process is pretty poor. And one of the things, several of the ones I looked at, you could have used a regression model or a micro simulation model. That I just don't get me going.
Right. Yeah. Okay. Thanks a lot.
Thank you so much.
Thank you. It seems there is no other question. As I already mentioned in the previous talks, and you see already on the screen as well, Alison's contact details are available in the events booklet, and she tries to answer whenever she can if you have a question for her. I definitely see potentials for collaboration. I'm sure many other people see it as well. So thank you very much again, and we will be in contact, I guess, in future. And now let's move to our next speaker. Anna Maria is our next speaker. Anna Maria Lasema-Korpinen is passionate about using data to answer questions in biomedicine. And she has a background in academia. She has worked in molecular biology group and bioinformatics group at University of Helsinki and also Finnish Institute for Health and Welfare. She later moved to the private sector where she is now, but she still stayed close to medical and health data. She worked previously at Terveystalo and Heinstop Performance, but now she's at Mehiläinen. And she is going to talk about data science for health and well-being today. Anna Maria, the floor is yours.
Thanks. Can you hear me okay?
Yeah, perfect. Yeah.
Perfect. So thank you, Seppinud, for inviting me already over a year ago, but here we are today virtually. This is great. It's great to be here, to have a chance to talk to you guys today. My topic is a bit changed, so I'll be talking about data science for smart digital healthcare. And I'll describe some of the work I've been initiating since recently starting at Mehiläinen. So Seppinud introduced me, but a little bit about myself. I'm a data scientist at Mehiläinen for almost 2 months now, which I'll get to more in a second. I've been working in the intersection of healthcare and biomedicine and computer science for over 15 years. In academia with my PhD in computational systems biology, and then pharmacoepidemiology at the Finnish Institute for Health and Welfare. And then now in the private sector for almost 5 years in healthcare, and then at Terveystalo as a data scientist and data analytics lead at Heinstop Performance, where that focuses on coaching and well-being for individuals and organizations. So if you're interested, feel free to connect on LinkedIn, although I'm not super active there. If you search for my name, it's relatively unique. So Mehiläinen. Mehiläinen is a leading Finnish healthcare provider and has a 111-year-old history here in Finland. It has customers including corporations, insurance providers, public sector, and of course, private individuals. And as I will soon talk about more, Mehiläinen is a pioneer in the development and adoption of digital healthcare solutions which is why it's especially interesting from a data perspective. The three main business areas at Mehiläinen are the private healthcare services, so physician services, diagnostics, operations, dental care, and working life services, so occupational health. Then there's the public healthcare services, so health centers with customers' freedom of choice, outsourced services, public dental care, emergency care services, and home care services. And the third area is social care services, including residential care services for the elderly and the disabled, mental health care, mental health rehabilitation services, and child welfare services. Mehiläinen has roughly 1.3 million customers annually in Finland, 540 locations here, and over 22,000 employees and private practitioners. And as a new flavor in November of 2020, so about half a year ago, Mehiläinen established a new company called Be Healthy to take our digital tools and platforms abroad and to focus on our international growth. And the growth strategy is has three areas. So first, the expansion into the core markets abroad, as seen here in green, with expansion, with actual purchases of clinics in those countries. And in these cases, we'll use the Mehiläinen know-how both in managing physical clinics as well as developing the digital services on site. Then in purple, you can see the sites where we've sold our digital platform as a software as a service provider. And this will enable a fast forwarding of the digital leap in those countries and those clinics. The third area for Be Healthy and our international journey are these chronic care pathways that are under development. These will serve both external customers and our current ones, and their focus is, for example, on developing care models for example, chronically diabetic patients. So overall, both in Finland and now growingly internationally, Mehiläinen has good capability when it comes to data, and we have good, clear aims to continually improve our services using data. And data quality and good quality healthcare with reliable data is something we're passionate about. And we have published our data related to quality in our Laatukenno, which is currently unfortunately only in Finnish. But let's see, we have published our data, for example, our customer satisfaction NPS values, availability, how quickly you can book an appointment or how long lab results take, safety, elderly care services safety, reported patient injuries, safety in surgeries, not prescribing unnecessary medicines that might use as narcotics, effectiveness, so for our treatments, for example, in diabetes care and dental care, and finally, our satisfaction of our own employees. And these metrics are constantly being updated, and we're developing new metrics as we speak to measure new relevant things. So go check this page out if you're interested, and feel free to contact me if you're interested in these. So even before the COVID pandemic, Mehiläinen was a pioneer in digital healthcare solutions. But as we all know, when the pandemic hit, it increased this digital demand immediately. And in Finland, Mehiläinen increased the capacity of our digital clinic and expanded these remote appointments that we have to cover the services of all our professionals. The number of users registered in the Oma Mehiläinen service, which is our platform name, exceeded 1 million in September, with visitor numbers multiplying from the previous years. And a total number of registered users currently is about 1.3 million. And in 2020, overall, the digital clinic became the largest unit of Mehiläinen instead of a physical location. And we've seen that the digital clinic hasn't cannibalized physical visits, but actually has fueled growth in the physical units as well. So what am I talking about when I talk about the digital platform? It includes tools for the professionals and administration side, but I will be focusing on the data collected from our digital tools for private individuals, and especially the digital clinic we have there. So through the digital clinic that you can access through your mobile phone or your web browser, an individual can contact a physician 24/7 and get quick access to treatment without making an appointment. So these remote visits can be used to treat symptoms and diseases that don't require a physical examination. Obviously, not all things can be handled virtually, but by visiting the digital clinic, you can also see what kinds of possibilities there are. So how the remote appointment starts, you start the window in the app and you select your main symptom category. So for example, here this client Yaba has selected these symptoms for respiratory infection, and then is asked more questions about their current symptoms. So here you're asked about shortness of breath, fever, other symptoms, any medications that you're currently on, any allergy medications and such. And at the end, it's possible to there's a free text place for any other descriptions about the current situation. This symptom assessment helps the physician work and improves patient safety. So for the user, it feels like a natural conversation they would have with a physician. If they would go to a physical location, these questions are the same questions the physician would ask them, but here they're delivered right in an orderly fashion, and then there's no worry that the doctor would forget to ask some of these questions. And users are quite used to using these kinds of chat type interfaces. Then for the doctor can see the data summarized as an anamnesis, and then especially important findings are highlighted. So for example, here, a high fever or difficulty in breathing, these can then be highlighted so that the doctor gets the information as quickly as possible. And you can imagine all the possibilities related to this kind of basic data visualizations in an anamnesis. There's additionally, of course, an administrative interface to create or modify symptom assessments. So if there's something not available, these can also be created. Then I will move on to the actual data, what it looks like that we're currently getting. Here's the virtual clinic number of visits per month that I'm working with currently. So the visits starting from the beginning of 2020 up to the end of May, which is a total of 730 visits. And here you can see the significant peak here in March. And down here is sort of the level where it was before this nice, lovely pandemic we're in right now. It slows down a bit during the summer, and then now seems to have leveled off at somewhere around 40,000 visits per month. Yes. And then for the symptom assessment usage, so not all visits to the digital clinic use the symptom assessment overall, and currently the data looks that it's sort of leveled off here, that about 60% of the so the gray is the visits with the symptom assessment. So roughly 60% of users who start the digital virtual visit use the symptom assessment dialogue. And what does that mean? So about 40%, there are the cases where you don't use the symptom assessment are, for example, when you're contacting customer service directly to reserve an appointment, or when you're renewing a prescription. But there's roughly 315 visits, 15,000 visits, of which have information about the symptom assessments. The majority of these symptom assessments are related to symptoms of symptoms of respiratory infection, so 65%, and that's a big chunk of the data. The other major symptoms that have high numbers of visit data are eye symptoms, women's urinary tract infection, and musculoskeletal symptoms. And these even only have 4% and 3% of cases currently. 25% of the data is then all the other symptoms that are reported. So rashes, diarrheas, headache, allergies, sore throat, and an other category, or if you don't find your symptom in the list of symptoms. And each of these has roughly 1% of the data mass that's been collected. And actually, I think the first thing probably for anyone working with data is to think about what kinds of diagnoses are these people getting. And actually, a colleague has previously developed a diagnosis prediction model with these symptom assessment data. And his findings were that due to the highly skewed data towards the respiratory infections, these respiratory infections were pretty well predicted. However, other diagnoses weren't so well predicted. And this is definitely something we're going to be looking into more. And since these initial runs were done about roughly a year ago, there's a lot more. There's a larger data set now available. So this is something that we will be looking into in the future. And right now, what we're hoping to do next is, instead of looking at diagnoses for these based on these symptom assessments, is to look for, start with a bit of a simpler model. And we will be starting a pilot where our goal is to develop rules for how to direct a customer directly to a professional that can treat them with the highest probability, or to find the best fit for a physician. And why is this relevant? So what we want to do is to have the smartest and fastest way of treating a client. So currently the times of the visit, we have an 8-minute median wait time for the first message. This obviously depends also on the day and time of the visit. So Monday mornings are especially busy. And then the other part is the majority of customers are cared by one professional during their virtual visit, and 12% are moved forward to one or more other professionals, for example, directed to customer services to reserve a time because it's something you need to take care of at a physical location. So this is the actual process of the virtual visit is what we want to start developing. And this was initiated because we have already 2 processes where we direct the patient to a specific type of practitioner. And we've seen promising results with these. So we have a specific symptom assessment for musculoskeletal issues, where the clients are directed directly to an occupational physiotherapist, so they can get assistance more immediately related to their musculoskeletal issues. And then we also have a worry chat where the customer is directed to an occupational health nurse trained for mental health. And both these changes in processes provide the customer with help faster, and these types of tools we want to develop for our other symptoms. this is sort of the data, the current status of this project, as I've recently just started, and a lot of work in progress. But the future work, and I'd be happy to discuss these ideas with the audience. The idea is to develop our data model to enable prediction of the type of physician to the patient. Is to develop the data model to enable the prediction of the type of physician that the patient should be sent to based on their symptom assessment results. And this will include data related to revisits and possible visits to physical locations. Then with these predictions, we can build up the physician capacity in the digital clinic to respond to the demands needed. So there needs to be actually those physicians in those specialties as digital clinic doctors. And like I previously mentioned, we will be doing this in an upcoming pilot. And then during the pilot, we can measure various metrics related to waiting times and conversation times and revisits, numbers of revisits. And we can look at how these metrics change and whether these predictions and physician assignments improved our metrics. So there's a lot of work still to do, and I'm sorry I wasn't able to present any results yet. But I have great colleagues that I'm working with in the team, and I want to thank all of them for all the help getting started with this work. So that's it for my presentation, and I'd be happy to take any questions and comments that come into mind.
Thank you so much. Okay, kiitos paljon for your talk. There is a question. Could you comment on how the patient data is stored?
Can you say that again?
Could you comment on how the patient data is stored?
Yeah, so it's stored in the cloud and in our own servers. So we have both on-prem and cloud resources for the data. And because the medical healthcare area is so highly regulated, there are quite a few sort of there are things that need to be considered when doing both data science, actual algorithms and analytics with the data, and also exactly that where the data is stored and how it's moved around is quite stringently regulated.
Okay, thank you. There is a question. I know you could open your mic and talk. Yeah, I think you should be all over. Yeah.
Okay, now I should be on mute.
Yeah.
Okay, awesome. Thanks a lot. So I was just wondering, you were talking about the big class imbalance when you're doing that symptom classification. I was wondering if there is like some issues with the traditional class imbalance techniques, why you cannot use them or they don't work in this case, such as synthetic oversampling or anything like that. You kind of comment on the class imbalance and how you could work with that.
Yeah. So this was actually this was work done by a colleague, so I'm not I'm not the best answer to all the details, but I think it was sort of a test run with a more classical classifier, and I'm sure that a lot of things could be improved just using somewhat more advanced techniques or different types of data balancing strategies. And
okay, thanks. Yeah, I was curious if there's like something like particular about the kind of like healthcare data where these kind of methods wouldn't work, such as like synthetic oversampling.
I don't think it's the case. I think part of it is also that how traditionally healthcare data is stored is not, it's not initially very usable for analytics. So there is a lot of data wrangling required to get the data into formats. For example, I mean, so the patient records are specifically designed to be patient records and not necessarily to be used for analytics. So, for example, in a lot of systems, the diagnosis may have especially before these days, maybe not so much, but just a free text field where without any checks. So for example, just getting the right formats of a diagnosis can be a lot of challenging work. So a lot of the data work that I've been involved in, actually all through my work in these biomedical and healthcare scenarios, are related to actually getting the data into nicely structured and format. So it's possible to do the actual analytics.
Sure. Okay, thanks a lot.
Thank you, Aina, for the question. If there's no other question, I have one. How systematically you're, I mean, again, related to the data, are recording the data, and is it like how much data you have on the patient's background and history and their diagnosis, and are you planning to do that for doing any diagnostics, smart diagnostics in future?
Yeah, so I mean, I think healthcare is so reactive still these days. So you come to the doctor when you're sick. So the type of data that's in patient records is data about patients when they're not feeling so good. So in that sense, the data is already sort of biased towards that. But we do have, obviously it depends how long a patient has visited Mehiläinen facilities. And obviously in Finland, you may go to a private healthcare, you may go to public visits. So our data sources are only the ones that includes visits to Mehiläinen. But there we do have access to their previous diagnoses. And I mean, obviously part of the medical, like part of treating a patient is understanding their previous diagnoses and underlying conditions that need to be recorded in the database. So things like that are quite relevant then to actually creating predictive models.
Okay, thank you very much, and thank you for your talk. And we are in time for our next speaker, Susanna. I think you're here, right? You're mute. And yeah. Yes. Now we have you.
Okay. Hey.
Hey. Okay. So let's start by introducing Susanna, and then we're going to have a very interesting talk. Susanna has a PhD in computer science from KU Leuven University in Belgium. And during her PhD, she has developed latent variable models for understanding language and images in social media and in e-commerce data. She has worked for NASA Frontier Development Lab as an artificial intelligence researcher. And also she has worked in Microsoft Research Cambridge on machine learning for optimizing environments for larger scale software development. She has also been awarded the Google Anita Borg Scholarship, and she currently works as a deep learning research engineer at Grey Parrot to help recycling monitor waste, increase the number of items correctly recycled, and aid the transformation of waste into a valuable asset. And this is what she's going to talk about today, which sounds very interesting. So let's hear Susanna talk about computer vision for waste management. And the floor is yours. You could share the screen.
Thank you so much. I will share my screen. All right. Can you see my screen?
Yeah.
Perfect. All right. So, well, yes, thanks so much for inviting me. Super happy to be here. So again, so I'm working as a deep learning research engineer at Gay Barrett. I'm going to be talking about computer vision for recycling and waste management. So the world is in a waste crisis, as we all know. We produce about 2 billion tons of solid waste every single year, and only 14% of it is recycled, and most of it actually ends up in landfill. And that's a picture of what these landfills could look like. We all know this represents a major environmental problem. We've seen all over the news. This is a problem we all need to tackle. So how can we help? Well, let me show you a little bit before how material recovery facilities work. So because these, they're in the middle of the process of recovering all these materials that we end up, putting in our recycling bins. So I just want to take you through a quick overlook. This could change from country to country, but hopefully this diagram gives you the idea of how these facilities work. So the main purpose of these facilities is to recover all valuable materials that end up in the waste streams. So there are trucks that bring all the waste into conveyor belts, and normally there are workers that pre-sort these belts. So they start removing any non-recyclable materials, any bulky items. They start removing them from the belts. Then the waste goes through several machines and processes to actually be separated. So we first sort out the cardboard. Whatever is left out might go into another stream, where other workers might be removing things that should not be there, that may have been missed by the first workers. So any contaminants or things that should not be there are removed, often manually, sometimes using other machines. But in the whole process, we start recovering paper, steel, glass, aluminum, and plastics. So yeah, this is sort of like the overview. So we obviously want that there's no contaminants in the recycling bins, because these materials end up being sold so that they can be reused to make perhaps new bottles or new cans. So everything that ends up in these bins need to be as pure as possible, without any foreign objects that should not be there. But also we don't want to miss any valuable objects. So we don't want that any plastic or any aluminum actually ends up going to landfill, because they're valuable and we don't want to waste them. So this is how they work right now. Let me show you a little bit more on what these workers, the people that work in the waste streams, actually the work that they do, because they do a very, very important job. It's really amazing what they do. It's a hard job. They have to be focused, they have to be fast, and ideally, they want to recover as much material as possible. I've seen some statistics that some of these workers actually work for very short periods of time in the facilities, because it's such an extraneous job, and because they're often exposed to hazardous substances. So you can imagine that it's not like a super fun job to do, although it's super important to do it correctly. So these are really amazing workers. So as perhaps I've already conveyed, but this status, or so this way of working present many challenges for the material recovery facilities. So as you can see, there's this reliance on manual sorting and manual sampling. And because of the way the process works, there can be some contamination, meaning the bins that are supposed to be recycled end up having things that are not supposed to be there, or we may miss some valuable items that end up going to landfill. The whole process ends up being a bit inefficient. We might lose some value. But most importantly, the facilities don't have live data streams that could allow them to make more informed decisions on how to optimize the plants, so that we start recovering everything we need to recover and don't lose any valuable materials. So this is where our solutions from Great Barrier come in. So what we're doing is providing data to the material recovery facilities so that they can have actionable insights. In particular, what we do is that we place monitoring units. So these are hardware boxes that contain cameras and lights and other kinds of sensors. And we place them on top of the conveyor belts, and they're recording images from the garbage as it goes through the waste streams. We use computer vision to recognize the objects that are going through the streams, and then we aggregate all the detections into a live dashboard that then allows the facilities to monitor the waste streams as they need. And from that information, they can, discover discrepancies, discover things that are unexpected, but also our APIs are open for robotic applications, where you can have a robot where, because we're detecting the materials in the waste streams, the robots can then help the workers pick out, the right items as they're sorting or they're sampling the waste streams. So basically, our mission is to actually digitize the entire waste streams so that we can automate and that we can actually go to a more circular economy where we don't lose valuable materials. So here's an example of what it looks like to sample the waste if we don't have, these monitoring systems. So normally in the left side, we can see what it would look like, how these sampling tables look like. So there would be workers standing here and receiving all this, waste, and then they manually would have to sort it into bins. And then they would weigh it to see how much, for example, plastic bottles versus cans versus cardboard are going into the waste. So by this process, because it's super manual and super time consuming, you could only sample 1% of the waste because of the restrictions I just talked about. But having, for example, one of our units on the conveyor belts then allow us to monitor 100% of the waste, so we can always have a live pulse of what the waste streams look like. Here I'm showing an example of this actually, or how we recognize. So as you can see, we're doing object detection, and this is actually in the residue line. So any material that is not supposed to be in the residue line, we detect it, and we give this information to the managers of the facilities, so that if they see, for example, oh, we're losing just too much, metal caps, too many of them, we better install, for example, a magnet on this belt, and that's the type of data and insights that we can offer them. Another use case that we have is actually, instead of only or on top of recognizing materials, like I've talked about, cardboard and aluminum and so on, we can also recognize products at the brand level, and sometimes at the SKU level, so individual products. So here, you could detect, Coca-Cola versus Pepsi versus Fanta, and this is actually super interesting for consumer awareness. So we could actually say, how many Coca-Cola bottles end up actually being correctly recycled versus how many end up in landfill, which is a very useful thing to know, especially sometimes for new products or new packaging, where if the packages are confusing to recycle, both for the consumer or for the plants, we could actually find that out because we're measuring and we are detecting these objects as they come through. So our approach. So what we do is we install these units. So here you can see a unit on top of a conveyor belt where this is done. And we capture images for a certain amount of time. We just collect lots of images from the facilities. Then we manually label them. So we send them to annotation companies to annotate them based on the categories that we care about. We train deep learning models, and then we deploy them into the real world. We deploy them directly in the box. So we have GPUs running in the box itself. So the detection all happens at the edge and not on the cloud. To give you some ideas of the things that we actually recognize, so this is constantly evolving. So in 2020, we were detecting about 17 different classes or 17 different materials, from aluminum cans, gray board, brown board, paper, and so on. And in 2021, so this year, we're expanding our taxonomy, or the number of labels that we can recognize, to include more different types of materials based on what the clients need. So as you know, our clients are these material recovery facilities, and we've worked closely together with them to figure out what are the things that they care about, what are the materials they want to or are important for them to recognize, so that they can have all the insights that they need. On the product brands, I'm showing some examples of the products that we can recognize. So it goes from Coca-Cola, Evian, Fanta, and so on. This is on the PET line. So this is one of the plastic lines from the PET. So the plastics are separated based on different polymers. So normally they have PET and HDPE. So on the PET line, these are some of the brands that are often in the streams. And in the HDPE line, which is another plastic polymer, these are some of the brands. So here you see more like milk bottles and that type of brand in the HDPE line. So some of the challenges that these things bring up is geographical variation. So you can imagine that the waste in Italy looks very different from the waste in Korea. And that waste in Korea looks very different from the waste in Venezuela. And this is because the products we consume, look different in different areas in the world. So that's one challenge for our computer vision systems. Another challenge is that there's lots of variations in distribution between different lines. So as I showed you before, the PET lines are one of the plastics. You can see certain brands of products versus another line, HDPE, you see a completely different distribution of products. And finally, or one of the other challenges that we have is the scaling of the target products. So initially, so I showed you, okay, we can recognize these 20, 30, or 40 different products, but that just represents a very small range of the actual products that could be out in the market. So as we know, there can be tens of thousands, even hundreds of thousands of different products that we could potentially be interested in recognizing to have complete accountability of what ends up going into the waste streams. So this is actually a problem that I'm personally working with on how to scale the number of products that we can recognize. So normally in computer vision, you decide the categories that you care about. You go and annotate data on those categories, you train your model, and then you deploy it. And then if you have new categories that you want to recognize, normally in the standard methods, kind of out of the box, you have to, once you have a new category, you have to retrain your model to recognize that new category. And so that's quite inefficient. So our goal is to actually have one model that can be deployed in all these different conditions so that it continues to learn as it goes. And then it also can scale. So every time it sees a new product, it's able to say, okay, I don't know, I've never seen this product before. I'm going to put it in my database. But next time I see the same looking item, I could recognize it. So this is a problem that I'm working on specifically. And sorry, yes. And one of the ways that we're tackling this is using few-shot learning. So in few-shot learning, you create models such that you only need to see a few instances of every class that you care about, so that the annotation efforts are reduced. Because as I mentioned before, it's very difficult to to always be annotating more and more data every time there's a new product that comes up. So for few-shot learning, we're looking at various architectures. So in particular, one method that we're looking at is using Siamese networks, where you have, for example, you would have a crop of a Coca-Cola bottle, and you would represent it in a vector space that we often call it an embedding. So here is the vector space. And you want that if you have another sample of Coca-Cola, while you're training, you impose in the loss function that the embeddings or the vector representation of these two items, that they're close together versus the distance between these items and other items that are not Coca-Cola. So this is one way of actually training in pairs or triplets to show the model what things should be close together and actually to cope with the lack of data. Another approach that we are looking at is using contrastive learning. And contrastive learning, the unsupervised version of it, you actually don't need to have labels, but you just need to have, you have images that are broken into, that are cropped in different, randomly cropped, and then they're also randomly augmented, and they're passed through convolutional neural networks to represent them in embedding space. And then you enforce that embeddings from the same images are close together versus embeddings of different images should be far apart. This is just to give you a little bit of a flavor of, of some of the methods that we're looking at. So after making all of this, making them into a pipeline and making it all deployed, this is an example of the type of insights that we can give to the material recovering facilities. So this is our dashboard, where you can, you can have live streams of the cameras in different lines, and then you can see, basically in real time what's happening. And you can have, graphs showing you the throughput, so kilograms per hour, that your facility is processing. You can see, the types of plastics, how many were contaminated, how many items that were not supposed to be there, how many were accepted, what was your target, how many items did you see, the weight, the value. So this actually is, it's a live dashboard that gives you a pulse on what's going on in your facility to make it more efficient. Then we do waste composition. So we say, okay, out of, in the PET line, how many actual clear PET bottles we found versus, versus other materials, or versus, trays, for example, or other plastics. And then again, this gives you information of the composition of your waste, so that if it's not what you want your streams to have, you can take actions. You can say what kind of hardware you want to install in order to avoid any discrepancy between what you're observing and what your target waste composition is. We can also detect some unusual events. This is actually some examples of things we have detected, is that, on a Wednesday afternoon at 4 o'clock on November 25th, we saw a peak in the number of products that were going through the conveyor belts. And if we compare to, another Wednesday afternoon, another time, this is not there. So this is quite unusual. So, we can enable the managers to then go into the data and say what happened during this period of time, so that, to see, what caused this unusual event. And this is only because we are monitoring the waste. We are, watching it, detecting every object, analyzing it, putting into a dashboard. So it allows us to have the metrics that we care about. So to conclude, I guess we all want a world where there is zero waste. We want a full circular economy where everything we make goes back into valuable materials that can be reused, recycled, and actually not going into landfills or other, uncontrolled areas. So one important step to do this is actually to start monitoring where our waste goes, what happens to it as it goes through the facilities where it gets processed. And this is what we're doing at Grey Parrot. We are digitizing the waste to help us get there. It's an ambitious goal, And working at Great Parrot has also helped me realize or think about more about what I put in the bins, how easy it would be to recognize them once they're in the conveyor belts. I think a lot about garbage lately, but it's important. So yeah, it's fun. So with that, I conclude my presentation. I'm happy to answer any questions or comments.
Thank you. Thank you very much. It is one of the applications of science that makes the world a better place to live in. So in that sense, it was very interesting to listen to you. So we have a question from the audience. Let's Aino talk. You can open your mic, I think.
Sorry, the meeting turned me out. May I ask a question?
Yeah, sure.
Okay, thanks. Thanks a lot. I was wondering, you said that for different countries, the waste profiles are very different, which I can imagine. So do you then always like train your models like from zero, or do you use transfer learning?
Yeah, so this is actually still an open problem because our goal is to have, to be able to have one model that could work in any location. And it is quite an ambitious goal because, as I said, yes, and as you mentioned, we know that the garbage, the waste looks different in different countries. So our current approach does include transfer learning and domain adaptation. So we still use the information from other facilities, from the facilities that we have gathered lots of data, and we train models on those. And then when we encounter a new facility that we've never seen before, or that the waste looks very different, we have to do domain adaptation and also transfer learning. But eventually, our goal is to have one single model that can cope with all these variations. And again, it's an ambitious goal, but that's a little bit what the team is working on.
Right. Okay, thanks a lot.
Thank you for the question.
Is there any other questions, comments from the audience? I was curious how many places, countries have adopted your solutions, how much you're closer to have a better smart waste management system.
So I believe, I don't know the exact numbers, but I think we're like in about 12 different countries. It goes from Korea, Italy, the UK. Okay, I don't know all the countries, but yeah, there's quite a few. I think it's like 12 different countries that we're operating in.
Yeah, I think it's really important. The whole world, nature and anything else needs these smart waste handlings.
Yes, it's very exciting to be working in this.
Yeah, definitely. Thank you very much for your interesting talk. And I think we have 5 minutes to the break, but if there is no other questions or comments, we probably can have a bit longer coffee break. So we will be back here at 14:45 to listen to our next speaker. Until then, have a nice coffee break. See you around.
See you.
Maybe I can already share my screen to make sure. Is it visible?
It is. Yeah, it is the full screen presenting.
The black hole. Okay. Good.
Yeah.
Good. That's what we're going for.
Okay, welcome back, everyone. We got to the final session of today's event, and I thank you for being part of the WiDS Turku event. Our next speaker is Cristina Casimero. She studied electrical and computer engineering, and she got her PhD in computer science at Delft University of Technology. She is currently a senior data scientist in Booking.com, and she has been, in her current role, she has been applying machine learning to problems such as dynamic pricing and fraud detection. She has also formed a team that is currently driving the development of an experiment tool for scaling up experiments beyond A/B and causal inference. Christina, the floor is yours.
Thank you very much for the introduction. You can hear me fine, right? I will assume. Yeah. Okay, great, yeah. Cool. Yeah, good afternoon, everybody. Thank you for being still here, and thank you for the great talks. It was actually really an enjoyable day for me. So I am Christina. Yes, I am a senior machine learning scientist at Booking.com, and today my talk is going to be relatively technical. I will talk about a new experimentation framework that we are about to deploy at Booking.com. In the presentation, I will explain why I picked the name MAS, besides being a cool name. But very briefly, before I get into the topic, I'll just explain how I ended up in the Netherlands. So I'm originally from Greece. I am from Thessaloniki, a city in the north of Greece, where I did my studies, my undergraduate studies. Then I moved approximately 10 years ago. I'm also revealing my age here, to Delft, a cute little town in the south of the Netherlands, to do my PhD in computer science. And afterwards, it was an easy transition a little bit north to Amsterdam, where I joined Booking as a data scientist, and where I've been working for the last couple of years on a variety of projects. So many of you might, or some of you might have already used the website of Booking.com, maybe to book an accommodation for your trip, or to get any type of assistance for your trip. In reality, Booking is more than an accommodation website. It's an online travel website company, where with the mission to empower people to experience the world. This means that in the website you can find pretty much a lot of aspects, hopefully all aspects that encompass our customers' travel. So you can find, besides accommodations, the flights, local transportations, attractions, experiences, and so on and so forth. Now, to make sure that we're actually providing helpful products and services to our customers to seamlessly experience the world, we need to listen to them with their data. And the way to do this is A/B testing. Now, every product, every tiny little feature in the website, every change in the customer service process, or every new machine learning model, before getting deployed to the millions of our customers, needs to first get A/B tested. I will be using the term A/B testing a lot, so I just want to clarify what it means so we're all on the same page. So A/B testing is basically a colloquial term for an online randomized control trial. So we have two versions, the version A and the version B, and then the online traffic gets randomly allocated to each of these versions. And then the version that is significantly better than the other in terms of some business outcome of interest gets deployed. So if every idea needs to be, so we are a big company with a lot of different teams, and if every new idea needs to actually first get A/B tested, this means that we have to run a lot of concurrent experiments on a daily basis. So yeah, as I say, you have more than thousands of experiments, which is a significant number. So in a way, it has turned into a way of decentralized decision-making tool. So everybody in the company, regardless of their background, if they have a hypothesis, they can run an experiment. And depending on the results of this experiment, they can also deploy it for all the customers. So this is actually pretty cool, very powerful as well. But of course, with power comes responsibility. So what we need to remember is that an A/B experiment is essentially statistical hypothesis testing. So there are some strict guidelines about how to perform this correctly, and the validity of the results depends strictly on whether people adhere to the protocol. Very roughly speaking, I will get, of course, into detail in the following about what exactly the protocol is, but basically people need to set up some parameters, an experimenter, to design the experiment. For example, what is the minimum effect size they need to see, or how long they should keep their trial going. However, often experimenters might make mistakes. They don't exactly misunderstand how to set up some of these parameters, or they forget, or they might get impatient. And of course, these accidents are they're accidents, and they are understandable because these people they don't really have the necessary statistical background to be able to understand how to properly run an A/B experiment. So that got us to realize that while A/B experimentation is a great tool for making decisions in a company, it can compromise seriously the validity if it is used strongly. So we need to probably try to improve it to make more rigorous, more robust to user errors, and maybe a bit more optimal so that we can make decisions even faster. So in the following, I'm going to use a specific example to explain a bit more what are the shortcomings that I see. First, I will explain what is the current way of running experiments, what are the shortcomings we see, and how we can address them with the max suggestion. So let's assume that we want to find an optimal website configuration. So we have different components there. We have destination, recommendations, accommodations, search boxes, and we need to position them around the page in such a way that the page is going to help the customer move forward to the next stages and eventually book. So we have the baseline, which is the current default version, and a couple of variants. So this is, well, a generalization of the A/B experiment that I described before. So it has, because it contains, it's an ABN experiment because it contains more variants, which is actually a very practical scenario to happen in a company. We have many hypotheses. So in this case, we have K independent hypothesis, null hypothesis. And for each of these variants, the null hypothesis is that it is significantly worse than the baseline, and the alternative that is significantly better. Now, what the user would need to do is set what is the minimum effect they want to see. And based on that minimum effect, they need to compute the sample size, the power calculation process, the minimum sample size that they need to have in their trial to be able to observe that effect size, to detect that effect size with a high probability. So this is the power of the experiment. At the same time, we also want to keep the false positives low. So we want to decrease the chance that you're going to see an effect when there is no effect. Typically, we fix this type 1 error, as we call it, to a low number, something like 10% or 5%. Just a little detail here, because we have K independent hypotheses instead of 1, we need to also account for the fact that we will conduct multiple hypotheses, and we need to decrease our significance threshold a little bit more per hypothesis to ensure that our family-wise error remains indeed at 0.1. This is a Bonferroni correction I've done here, but you can also do other corrections. That's just this is something that's taken care of by the tool, by the way, but I just wanted to get it out of the way. Now, after we know the sample size, then we distribute the traffic uniformly to each of these variants. We wait until n samples have entered the trial. And then in the end, we do our t-tests or chi-square tests, whatever. Let's say it's a binary metric. So we will compute the p-value for each of these hypotheses, for each of these variants. And low p-values are good evidence that the null should be rejected. So if the p-value for each of these hypothesis is lower than alpha, than our corrected alpha, then we deem these variants to be better than the baseline. That's how, this is pretty simple, pretty intuitive, and this is pretty much how experimentation works in a lot of companies right now. There are certain problems, though, with this. Some suboptimalities and some problems. So the first thing that is suboptimal is the fact that we need to sample uniformly. Now, let's assume that we actually know what the means of these variants are. So now here, imagine that I'm measuring, let's say, conversion. So each of these news here is the average conversion, let's say, per configuration. So in this case, the baseline is 0.1. The first variant is very close to the baseline. The second variant is much higher than the baseline, and the kth variant is much worse than the baseline. So with this information, it makes a bit more sense if I actually start sampling a little bit more towards the more promising variants. So that would be the variant 2, that is more prominent for being the best one, and much less to the worst variants, and then maybe distribute the traffic uniformly between the base and the variant 1. Of course, the problem is that I don't know a priori what this means, and as a result, I do need to find a way to iteratively adjust my sampling as more data comes in. So this is a challenge. The second problem is that the users are not allowed to monitor. And what we mean by monitor here is that people would like to be able to view the results of the experiment as time goes by, and based on the results, decide whether they're going to continue the experiment or not. So why this is not allowed with this current setup is because we consider we're going to have one hypothesis, but if we are constantly conditioning on whether we're going to continue the experiment or not based on the previous data, we're conducting essentially multiple hypotheses, and we're not correcting for this in the right way. So actually, if I show you how the evolution of the p-value would look under the null hypothesis, so here I have a Bayesian variant that are equivalent, equal to each other. So we're not supposed to see any effects, but the p-value is almost sure that at some point it's going to drop below a significance threshold. So here it actually drops 3 times. So if I were to pick the first time the p-value drops below the threshold and just deem the variant significant, I would really make a lot of mistakes. So this doesn't say that we shouldn't be doing monitoring. It does make sense that as the data comes by, they bring information, and I should not be ignoring it. But I would need to correct properly in a proper statistical way to be able to do this correctly without inflating my false positives. And then the third problem, but not definitely very important problem, is that the answer that I got from my testing was not the answer that I was looking for. So when I started, I said that I want to find the configuration that is the best. But what this multiple hypothesis testing returned to me is that the variant 1 and the variant 2 are significantly better than the baseline. But what I wanted to actually know is that the variant 2 is the best. This is to say that actually in business, we very often have different problems. So yeah, sometimes we want to optimize. We want to just find and deploy the best option, as we do, for example, with the website layout. In other cases, we might not even want to deploy a change, and we just want to learn, or we want to get inspired, or we want to combine the results that we get from an experiment with external data and see whether it fits in a bigger picture. So here, for example, the team wanted to add a new copy for the filters, and they just wanted to get inspiration, and they were interested in looking at all the promising variants that are significantly better than the control to combine them with some user research data. So in this case, we would be interested in seeing all the variants that are significantly better. And in other cases, time is of the essence. So we just want to be very quick with a decision. Maybe we don't have the time to wait until we figure out that a variant is the best out of all. We just need to get anything that is better than the baseline. This can happen because we're quickly solving pain points. We have a deadline. Maybe there are bugs. Maybe for any reason, we need to make a fast decision making. So here, we would just need to take any arm that is significantly better. However, now, with all these problems, though, at the moment, despite of these different business problems, people can get a specific answer that the tool is giving to them. So this is essentially a pretty big problem, because everybody needs to start thinking in terms of what the tool outputs to them, but this is not what a measurement tool is for. So for all these reasons, we took all these problems together, and then that's what we hope that we are addressing them with the MASS experimentation framework, which stands for multiple problem, multiple hypothesis, adaptive sampling, and stopping. And I will give you a little bit of more, a a flavor about how we get inspired to solve these problems. And the main inspiration for the solutions comes from the multi-arm bandit literature, specifically for pure exploration. Some people, or maybe most people, are more acquainted with bandits for reward maximization, in which the task is that I want to find the particular variant or the particular arm, I will be using them interchangeably from now on, that will maximize the cumulative reward. Now, because we want to maximize the reward here, or minimize regret, our policies need to very carefully balance between exploration and exploitation in order to be able to achieve that objective. However, in our case, we don't really have any reward constraint. We're going to run the trial for a finite period of time, and then the best solution is going to be deployed for everybody. So there's no really cost in exploring. In fact, we just want to explore. We just want to learn the statistical properties of our arms. So that's exactly what pure exploration does. So pure exploration is a statistical hypothesis testing, which gathers all the characteristics that we're looking for. So it's multiple. Composite. Composite means that we don't know exactly what the alternative is. Sequential, that means that we can stop adaptively on a data-dependent moment. And active, that means we can sample as well adaptively. So each of these components fit exactly very nicely into all the challenges that I described before. Now within this pure exploration problem, we can define like these sub-problems that you can also map to the business problems I talked about earlier. So the best arm identification, in this case, I'm looking for a second arm. If I start counting from the 0, all arms better than the control. In that case, I would like to see 1 and 2, or any arm better than the control. In that case, either arm 1 or 2 would do. So for all these problems, the objective is that I want the algorithm to return the correct answer to me, keeping the error low. Usually we pick a delta which is 0.1 or 0.05, and as fast as possible. So these are the constraints. Now I will describe a little bit about how the adaptive sampling and stopping would work, specifically for the best arm identification problem. There are similar ideas could be applied for the other problems, but the other problems are not solved yet. So I will tell a bit more later about that. Now, let's say that we want to sample adaptively. We could find a lot of heuristics actually to do that, to adjust the sampling based on the problem that we want to solve. But there's one optimal way to do it. The idea is that if we know if we know the model we're working with, that means we know the distribution where the model comes from. So it's a binary variable, and I know the means of each of the arms. Then there is an optimal way to sample. And actually this optimal way in this particular example matches the intuition that we had. So here, the optimal way to sample from our example is I need to sample 40% the best arm, 2% almost practically not at all the worst arm, and around 29% equally the baseline and the very close variant it has. However, again, we do not know these averages, so we need to estimate this mean. So we need to do this, we need to be able to work with data as it comes. So therefore, we need to use an algorithm that can actually guarantee that we will converge to these optimal sampling proportions with more data. So the algorithm works as follows. So it computes actually these proportions based on the empirical means that we have observed. And then with the right exploration, it is guaranteed that we will converge to the empirical proportions, to the optimal proportions, sampling proportions. So here I'm actually plotting how these proportions would look over time in such an experiment. So you could see that already the W2, which is the second variant, the best, and the worst, the W3, the algorithm already converged pretty soon to their correct values. It had a little bit more trouble distinguishing between 0 and 1, but eventually it did. So this is approximately how over time the algorithm learns how to sample optimally with the data. Of course, if the problem was different, if it was all better arms identification or any better, then we would use a similar approach, but then these optimal proportions would actually be different depending on the problem. And of course, we also need to find a way to stop. So here the idea is that how can I, observing the data, find the right moment to stop without inflating my false positives? This is a non-statistical question. Dates back. This solution dates back to the 60s with Chernoff, actually, with a generalized likelihood ratio test, which is used basically for sequential testing. So the idea is that we now want to construct a test statistic over time and to stop when there is no plausible alternative model in which the correct answer that we're returning is actually wrong. So specifically, this is a log likelihood. This ratio basically represents the maximum likelihood that the data we have observed so far comes from a model where the reported answer is the correct answer. X here would be the data we have observed so far. And it's divided by the maximum likelihood that the data comes from a model in which that answer is not the reported answer is not the correct answer. So you can imagine a different model where the second variant is not the best now. So with this definition, if we are pretty sure that our answer is correct, it means that it's very likely that the data comes from the correct model. So when the GLR statistic is large, then we want to stop. But how large should it be? We don't want to be very conservative because then we're not going to make a lot of mistakes. But at the same time, we also want to be able to stop as early as possible. So there has been a lot of work, including recent work, about trying to find a tight threshold that depends on time and on the number of alternatives and the significance and the confidence parameter. but so as to not to minimize the runtime or the sample size, but while actually guaranteeing that the error rate will remain low. So here you see in the plot, I've plotted both the threshold and the GLR statistic, and both you see that they change over time. So when these two meet, then this is the moment that we're going to stop. This is actually nice because this now allows the user to pick. They can check the experiment beforehand, before its termination. Of course, we don't risk anything because before its termination, there is no answer reported. So we're not risking inflating the false positive. And they can decide that they're not looking, they didn't find the effect they wanted to see. So the experimenters can actually stop the experiment. Another good thing is that, of course, we can plug it in different algorithms. So it doesn't have to be coupled with an adaptive sampling. We can also use adaptive stopping with uniform sampling. However, if it's used coupled together with the optimal adaptive sampling, then we're also guaranteed that we're going to finish the experiment very quickly. Now, as I already mentioned earlier, so the best harm identification problem is a well-studied problem, especially the last decade. So the optimal solutions exist for that. However, for the other two problems, they're quite recent. So we already submitted a paper on the all better arms control problem, and we're working on the any better arm problem. And probably there are many other problems, so it's going to be an interesting additions for the future. So to solve that, these problems, we work together with some leading researchers in the field from Amsterdam and France. And we are excited to see what's coming next. If I can summarize, we're using all these insights from the research to basically provide an experiment tool that is more optimal in terms of runtime. So it can run faster, it can finish faster because it uses adaptive sampling and stopping. But at the same time, it releases the user from the burden of having to design the experiment and decreases the chance as a result that we're going to have mistakes because of the users. So now there's a lot of freedom for our experimenters to run experiments without risking making mistakes. They can pick, they can stop earlier, and they can get the right answer to the problem without having to tweak their business problem to what the experiment tool can give to them. Hopefully this can give inspiration to maybe others as well to improve their experimentation platform and help their users. This was my talk. I'd be happy to have questions either here or to connect also and have a discussion later or email or in LinkedIn. Thank you.
Thank you very much, Christina. Is there any question from the audience, either in Q&A or does anybody want to talk? I think they probably need some time to process.
Yeah, it's a little bit, I feel it's a bit more heavy.
Yeah, but it was very interesting, and you find a very comprehensive solution to a difficult problem. So you're ticking a lot of boxes in that sense with your solution.
That was the final, that was the idea, to answer yes to all the, to pick carefully each of these entries.
Yeah, that's true. Thank you very much. I think we can move to our next as our final speaker. And I see Helena is already here. Let's get... Hi, good morning for you. Thank you very much for being here this early. Helena is with us from Boston, so it is pretty early for her. So our next speaker, as I said, and I'm not sure if I'm pronouncing your family name correctly, Helena. It is Helena
Deus.
I don't know.
Deus.
Yes. Helena Deus, yeah, sorry. Received her PhD in computational biology, where she focused on knowledge graph-based management systems as enablers for translational medicine. And she's passionate about finding data science and technology solutions that could significantly accelerate innovation in translational medicine, with a particular emphasis in oncology. And she's currently a data science manager at ZS Association, where she leads biomedical semantic solutions. And today she's going to talk about data science as in support of biomedical research. Floor is yours.
Thank you, Sepinut. All right, so let's share my screen here. Is the screen sharing okay?
Yeah, that's fine.
All right, so even though nowadays I'm much more in the realm of data sciences, I started as a biologist, and in the back of my mind, biology is always present. It has huge implications, not just for healthcare, but also for our ability to maintain sustainability in this planet. We're going to need it for many years to come. So today I thought I would talk to you guys a little bit about some of the still existing challenges in data science for biomedical research, things we could do as data scientists to support biomedical research and biomedical researchers. But before we go there, I want to tell you a story. When I was very young, my sister was diagnosed with leukemia, and her doctors did everything they could to save her life, but unfortunately she was too small, and there was no way that they could do a bone marrow transplant, and so she unfortunately passed away. But of course, as you can imagine, that had a huge impact in my life, in my career choices. And the more I learn about data science, the more I am convinced that we really cannot address healthcare, significant challenges in healthcare without machine learning, without AI. So how are we going to do that? And why is biomedical research, why don't we have a cure for cancer yet? And part of the problem comes from the fact that the way scientific publishing still works, the way scientific communication and scientific discoveries are communicated is still heavily dependent on human beings. So we write papers for others to read. We don't write papers for machines to read. The problem is, as new platforms for publishing become available nowadays, you probably aren't doing your research by reading a paper, by reading journals, physical journals. You're probably reading online PDFs. And the problem with that, of course, I mean, it's both the problem and the convenience is that now you've got so many different platforms on which to publish. There's still a lot of peer review, but the scientists are freer than ever to put their scientific achievements out there. And that also creates a lot of noise, as you can imagine. Anybody can say anything on the web, and that's one of its core principles, but it also means there's a lot more noise in terms of how much we can trust the scientific facts that are made available to us. Add that to the fact that even through normal journal publications, and this statistic comes from PubMed, a new medical paper is published every 20 minutes, right? Which means if you put yourselves in the shoes of an oncologist and you want to make sure that you're in the top of your field and that you have the best possible solution to help every single one of your patients, you can't, because there's so many papers, so many things being published every single day that it's practically impossible for you as an oncologist to actually stay on top of your field. So it used to be the case that a single brain could digest the information available, the scientific information available, and come to their own conclusions and make their own decisions about how to treat patients. But we're getting to a place where even committees of individuals, multiple brains working together, aren't able to keep pace with every piece of information that could be potentially relevant for their decision making. And so the way I explain this to doctors who are still often hesitant to start adopting machine learning and AI is I tell them, look, imagine that it's a giant network of brains all connected together, helping you make decisions. It's not replacing your role in healthcare, machine learning is actually going to augment your role in healthcare. It's going to mean being able to use machine learning. It's going to mean you being able to have access to the most comprehensive information you can get your hands on, instead of just relying on what your interns are able to read on any given day. And that is, in my opinion, the way to talk with some of these domain experts that are really hesitant to trust the outputs of machine learning and AI. All right, so I'm also here to convince you that some of the aspects behind machine learning, in particular NLP and image analysis, are becoming commodities. So you, for example, you go to archive or you go to nlpprogress.com, and what you'll find is, for most of the typical tasks of NLP, or the commonly needed tasks of NLP, like recognizing entities in text, or classifying sentences, or co-reference resolution, parts of speech, there's so much advanced, especially in the last couple of years, since transformers and BERT became available. We're seeing accuracies of 96, 98%. We're seeing really, really good results in general purpose text. So in a way, machine learning is becoming a little bit of a commodity, especially as far as doing extraction of information from articles to really help build that knowledge engine that we need to help to augment the oncologist. What that means, in my point of view, is that increasing the accuracy, let's say, of co-reference resolution from 80 to 82% is not going to have as much impact as using these pre-existing, pre-trained models as tools in our toolbox to actually solve some of the more complicated problems, some of the problems that don't rely on don't have yet very, very large training sets. So the challenge, and I like how Andrew Nick articulated this a few weeks ago on Twitter. He said, most academic benchmarks hold the data fixed, right? And I'm sure a lot of you are very familiar with competitions on Kaggle and the grandchallenge.org, and there's a bunch of other websites nowadays generating data science competition. I'm sure a lot of you, that's how you learn the data science that you know. And he says, hold the data fixed and let the teams work on the code. Thinking of organizing something where we hold the code fixed and ask the teams to work on the data. Because in fact, in my experience, that's what's lacking. We've got so many awesome algorithms already, so many models, so many techniques of building highly accurate models, but we keep focusing on experimenting with those models on the same data set, whether it's ImageNet or the IMDb sentence classification, or there's a lot of data sets that are made available on Kaggle, and those, it's great that they're there, but it also means those are fixed, those are solved problems. And I'm really much more of an innovator, so I like the idea of going after unsolved problems. But of course, as you know, as always, the bottleneck is, where do I get the data? How do I make sure that my data is ready for me to use while training a machine learning model? We all hate that part, right? We all hate having to do data collection, data cleaning, data normalization, just so that we could use it. But the reality is, the machine learning is a commodity, right? And so if you know how to do machine learning, if you know how to do deep learning, and you clean and you have a clean set of data, then you're going to be the winner of that particular problem. You're not going to obviously wait for somebody else to apply your machine learning on your data, right? So if you own the data, then you're king, right? You're queen, right? You really own the insights that data set has to give you. So with that said, let's turn our focus a little bit into biology and biotechnology. As you saw from COVID and the whole pandemic, the people who got us out of it or close to out of it were the biologists, right? Because they understood how the virus worked and they understood how our body worked, and they built a vaccine that was able to be utilized by our body to fight the virus, right? So I have no doubt that in the next few years, we're going to really see a huge jump in our ability to change the way we work, to change the way we live through biotechnology. And so I found this nice quote online. Our world is built on biology, and once we begin to understand it, it then becomes technology. So much like a few years ago, we were all embedded in the computer revolution, I do think that pretty soon we're all going to be embedded in the biotechnology revolution, and it's going to sneak up on us. So my advice to you is get involved, right? Don't wait to get involved. Get involved now. Not only is it extremely important for our ability to survive on this planet and for our ability to cure disease, but it's also extremely exciting and a fun area to be in once you sort of have an understanding of what it's all about. So let me tell you a little bit about how to think about this problem. Nowadays we know this. We've known this since very ancient times. Our DNA, our genetic code, has everything it needs in order to create a human being, right? So generally translated, if you think about this as an encoder problem, the genetic code has the information to encode for proteins. The proteins have information to encode for cells, which in turn have information to encode for organisms like ourselves, which in turn have the information to build ecosystems, right? So an ecosystem is not built in isolation, it's actually built by life. Now, the further to the right you go on this scale, the more complexity you're going to find. So there will be all sorts of emergent properties that arise at every one of these levels that are fairly difficult to control when you get to the high complexity level, right? We've got plenty of examples of that where people try to control the ecosystem, but instead created more problems than they solved. Secondly, the closer you are to the genetic code, the more control you have. And I'm sure every single one of you at this point has heard about CRISPR. And CRISPR is nothing but a gene editing tool. You can pick a piece of DNA that you want to just cut and add a new gene, replace the gene with another. So it's literally our ability to control the genetic code. But as you can tell from this diagram, things don't always work as we intend them to work. So simply adding a gene, even if we know what that gene is supposed to do, doesn't guarantee that the cell will behave exactly like we want it to behave by inserting that gene. And therein lies the importance of machine learning. Because if you think about it, at the end of the day, these are all inputs and outputs. Your input is the DNA, your output is the behavior you want your cell to have. So what becomes critical in this view is you have to have the ability to know how to exactly change your DNA to get the desired behavior, right? So if you keep your output fixed, you have to find a way to change your input so that you generate that input. You basically need a mapping. So in order to make this more tangible, let me tell you a bit about a story about, it was a human intelligence story, and hopefully it'll help you guys understand how then to take some of these human intelligence stories and go ahead and build the algorithms to automate them. So this little girl is Emily Whitehead. When she was very young, she developed leukemia. Her parents, took her to the doctor. She had her cancer relapsed twice. So the first and second time she was treated with chemotherapy, and her cancer relapsed. By the third time, her parents were getting ready to take her to hospice. She was so sick that she couldn't handle another round of chemo. But her doctors were not ready to give up. And so they found this trial using a very, very new therapy that was called CAR-T, which in essence is application of CRISPR to modify a person's immune system to learn how to detect and destroy cancer cells, which is pretty neat. So they enrolled Emily on the trial, but she had a very, very bad response. She immediately went into a coma, and her doctors were ready to throw in the towel. Now, in parallel, one of her doctors, Carl June, his daughter happened to suffer from juvenile RA, and his daughter was taking this drug called tocilizumab to help with her rheumatoid arthritis. And Carl June knew this, right? He knew that there was a drug approved for young people, and this drug happened to be an IL-6 inhibitor. Now, when they measured Emily's blood levels, when they did blood tests on Emily, they did find out that one of her cytokines, IL-6 is called the cytokine, was expressed 100-fold higher than in normal people, right? So they had a pretty strong hypothesis that this was the cause of her coma. Her immune system had gone berserk. It was just basically attacking her normal tissues. And so Carl June thought, hey, I've got an IL-6 inhibitor here. I know it works for kids. Let's try it. And it did save Emily's life, right? Not only did she wake up from her coma, but she's been I think at this point more like 9 or 10 years cancer-free. And this was serendipitous, right? It just happened that Carl June knew that there was a drug that was approved for kids that may help Emily, right? So this is what human intelligence can do. These are insights that human intelligence brilliantly comes up with once in a while in order to make progress in the world. And thanks to this story, nowadays CAR-T are regularly used for leukemia patients. And not only do they kill the cancer cells, but they keep killing the cancer cells so that the cancer doesn't come back. Now, why am I telling you this story? Because simply, if we want to get really, really good at building AI systems that help us solve real-world problems, then we need to understand how human intelligence works in order to build artificial intelligence. So let's talk a little bit about my favorite topic, knowledge graphs. All right. So where does this data for the human intelligence comes from, so that we can then use that same data to build artificial intelligence? Say I ask you a question. Let's pretend I'm Carl June and I'm trying to answer this question. Is there a drug that can be used in combination with this CAR-T therapy that Emily was given to prevent adverse events? So in other words, I don't want to have to wake up Emily from her coma. I want to prevent the coma in the first place. So in order to answer this question, you have to first break it into sub-questions. Like, what is the mechanism of action of CAR-T? How does CAR-T work? What does it do? Secondly, can you measure? What can you measure based on that mechanism of action? What can you measure to forecast any adverse events that the patient might have? Number three, is there a drug that can be used to reduce these adverse events? And you may want to know if this drug is commonly used in combination with the therapy. Right? So based on these 4 questions, you then identify what are the types of data that I need? What are the entities? If this was an NLP problem, what are the entities in text that you're going to be looking for in order to answer each of these sub-questions. And what are the relationships you need to look for between those entities? So for example, definitely a therapy. You need information about therapies because that's what CAR-T is. And you need information about their mechanism of action, like the immune response activation. Then you also need to know if there's a database of drugs that inhibit certain proteins. Like in Emily's case, you're looking for a drug that inhibits this IL-6 protein that I told you about. And you want to know if these drugs or if these proteins like IL-6 are responsible for any known adverse events. Now, this data, unfortunately, it's not all neatly organized in a single database. Just for this simple knowledge graph I'm showing you here, you need to go after at least 4 different types of databases. FDA databases, databases that articulate how biology works, databases of therapies like real-world evidence databases where information about real patients is captured, etc. So not super easy, not as easy as downloading 3 gigabytes of data from Kaggle and running a machine learning model on top of it, but doable, because if you do come up with this, if you do aggregate this data set, then solving the machine learning problem belongs to you. So I spoke about knowledge graphs, and you may be wondering, what are they? Why do I need them? What's the point? And one point I want to make is that, and think about your own education. As you're going through classes and like studying the coursework, you'll realize that every insight you got in your life was not driven by data. It was not by, you didn't get an insight by reading a million papers and coming up with and realizing something, right? It's the intuition that you built. We read papers and we read books and we do experiments to build the intuitions that will generate the insights. So it's not looking at a million examples of cats that a child learns to identify a cat, is by developing the intuition of what a cat is, of what makes a cat, right? So much so that they only need to see 5 or 6 cats so that they can learn to identify a cat. So intuition, and I don't know how to, I'm not going to try to define what it is, but it can be captured in a knowledge graph, or at least parts of it. Because what a knowledge graph does is it captures relationships between things, whether they're people, events, organizations, cells, genes, proteins, signaling pathways, etc. I mean, think of the web. That's a massive knowledge graph. So that's what a knowledge graph is. It's an attempt to capture that intuition that's missing when we are often trying to train our machine learning models using data alone. So a bit of history behind knowledge graphs, just to get you guys to understand the idea a little better. So it all goes back to Tim Berners-Lee, and if you don't know him, he's the guy that invented the web originally. He invented the HTML standard. And in 2001, he wrote an article explaining that he never meant to create a web of documents. As you know, nowadays, when we go on Google, we get back documents, and documents are not an answer. Documents may be a gateway to the answer, but they're not the answer. And what Tim Berners-Lee's suggestion was, originally, he wanted to build a web of data where you can create a structured query and the system would automatically give you the answer. Not a document to read, not a bunch of documents to go read, but the most trustworthy answer to your question. So a bunch of computer science got inspired by this idea, and they started creating standards, because in order to transform the current web into the semantic web that Tim Berners-Lee proposed, you actually need to start capturing the data in a standardized form. So in the web documents that we have nowadays, you'd have to identify where are the entities and where are the relationships as an author of the document, so that crawlers can then crawl your page, look for the answer they need based on the user request. Then in 2012, and there's a really nice video about the Google Knowledge Graph that I recommend you guys go look at. But Google came up with their Google Knowledge Graph. They announced it, and everybody was excited. So basically what they did is they manually created a knowledge graph that nowadays every time you go to Google, if you do a somewhat standardized query like Paris, for example, you'll see a knowledge card on the right. That's the knowledge graph, the Google knowledge graph in action. Of course, the name stuck, right? We used to call it semantic web. Nowadays, we call it knowledge graphs because of Google. But in essence, in industry, knowledge graphs are being widely used, for example, to do master data management. In other words, how do you actually link data across disparate data sources, like the ones I was showing you at the beginning, the FDA data sources and the biological data sources, etc. We're also using text knowledge graphs a lot for text mining, because if at the end of the day, a knowledge graph contains the structured knowledge you need to make decisions, then documents contain those tidbits of knowledge. So you can actually use the knowledge graph to help with your entity recognition and your relationship extraction. And finally, what's starting to happen, and we're not yet there, but knowledge graphs give you a way to create explainable AI by letting you do two things. One, link the output to the input. So even if you don't care about figuring out what the neural net is doing and which nodes are being activated, you can still try to find out why is it that the algorithm said it's blue based on the input. So the knowledge graph gives you enough information for you to link the output to the input, therefore creating explainable AI, because now you've got a chain of evidence to follow. But the other thing that I already see people doing is trying to map the active nodes in a trained neural net with nodes in the knowledge graph. And that's a little harder, but it seems to be a very promising space as well for explainable AI. All right, so I'm running short on time, so I'm going to jump, I'm going to just skip this slide and kind of give you a few ideas on how to use, how to solve what AI tasks are there in life sciences still. You know, if I manage to convince you to, you know, focus a little bit of your time and attention in this type of problem, what are the problems that you could focus on? And these are just a few examples, right? But for example, can we harness the energy of the sun more effectively than we do today? As effectively as plants, right? Plants do it all the time. They take in CO2 and produce O2, right? So you've got that added benefit. And not to mention, they are able to produce massive amounts of energy using just the sun. Can we recycle food? Can we produce food and its byproducts in a sustainable and robust way? Or can we identify new drugs or treatments for cancer? So again, I'm just going to try to open up the problem for you. I'm not going to try to solve it for you. That just to give you an idea of how we could do this using machine learning, using those techniques that you're already so familiar with. Now, let's take a plant, right? A plant uses sunlight, uses carbon dioxide, uses water, and outputs oxygen. If you double click on one of the cells in this plant, and then you double click on these little tiny things you'll find inside the cell called chloroplasts, what you see is this complicated chain where light comes in, and then there's some electrons being activated and CO2 being utilized, and then at the end you've got this creation of energy in the format of this thing called ATP, which is basically the life's battery. It's where energy gets stored. So how would you understand this using AI? One way you could experiment with, and I haven't experimented with, but this is just one idea, is if you take your input vector to be the DNA sequence of that cell, right? As I told you, all that information is encoded in the DNA sequence. You can take the amount of luminosity that your plant is exposed to, the amount of water that your plant absorbs, and the amount of CO2 that your plant absorbs. These are all things you can do today with the proper equipment in the proper lab. You can train a decoder model to output these energy units and the O2 that this plant produces, right? Now, you your decoder model, and you won't know it until you try to explain it with the knowledge graph, but your decoder model will be learning the biology, because at the end of the day, yes, there will be a neural net that will have some nodes active and some nodes inactive. But at the end of the day, if you're able to predict very accurately what your input vector, how your input vector gets transformed via, linear algebra of deep learning networks into the output vector, basically what the model has learned is biology, how biology works. So instead of the guessing game that biologists have been trying to use to decode biology, this is a much more effective way of actually understanding how biology works with resort to computers. All right, let me just give you this last problem, and because I think it's, for me, it's the more interesting one to solve, which is, can we identify new drugs or treatments for cancer? Now, let's say there's a person and they have a melanoma, skin cancer. When you zoom into that skin cancer, what it looks like is this ugly mass that has like blood vessels all over it. And how did this, if you double click on one of these cancer cells, and I'm kind of on the right here showing you the difference between a normal cell and a cancer cell. A normal cell is constantly emitting signals. When it's hungry, it emits a signal into the bloodstream saying, I need oxygen, I need food. Or when it's low on oxygen, is emitting a signal through the bloodstream saying, I need oxygen. And so the immune system, you probably are familiar with the immune system as the system that comes and attacks our pathogens, but it has a much bigger role than that. We know that nowadays it actually plays this role of helping to build blood vessels so that cells that are in locations with low oxygen and low food get more blood vessels, right? Get exposed to more blood vessels, therefore being given more oxygen and more food. Now, another thing you might know is that our cells actually have a mechanism when they're damaged, and damaged cells happen all the time. Every time you get a sunburn, what the redness in your skin means is your cells have died, right? Your cells have been damaged, too much radiation, too much damage to DNA, and they basically have been destroyed by your immune system, right? Your immune system is able to read that signal, I'm sick, come kill me, right? When the cells are damaged. Cancer cells are cells that not only are, even though they are damaged, they do not send that I'm sick signal. Instead, they hide the I'm sick signal and they optimize towards sending the signal, I need more oxygen, I need more food, because they are growing more rapidly than normal cells. They are damaged. And the immune system takes that as a message to build a lot more blood vessels, right? And this is why you end up having, when you look at tumor in medical journals, and I don't recommend you do that because it's gross, but a tumor is typically surrounded by blood vessels. And that's all the work of the immune system, because the immune system is reading the signals. It's trained to recognize need food, need oxygen messages as a message to behave in a way that creates more blood vessels to feed that tumor, right? When in fact, what you really want is for those immune cells to actually recognize that this signal should actually be associated with cancer, not with a need for more blood vessels. So that's what I propose we could experiment with. So if you take as input the DNA sequence of these immune cells, as well as the signals they're hearing, as well as the drug you want to experiment with, and your output is the behavior, right, to destroy or add more blood vessels, then at the end of the day, what you have is a decoder model that is able to turn that's able to explain how DNA gets turned into this behavior. So in order to find the optimal drug to use to destroy cancer, or to find the optimal way of engineering those immune cells, right, is by trying a bunch of different outputs and observing which ones actually have the behavior that you want when the signals match those that cancer cells tend to release into the environment. All right, so I just want to kind of conclude here with a few things. So one is machine learning is becoming a commodity. And you know this because I'm guessing the majority of you have downloaded pre-trained models and architectures from GitHub and used them in your problems. Second, in the land of messy data, the woman with the clean data is queen, right? And I see this a lot, and I hate when I see this. Just people go ahead and they prepare their beautifully clean data. They put all of the effort in doing the clean data, and then they go and ask the machine learning engineer, typically guy, to do the analytics for them. It's like, no, that's insane. I mean, it's a commodity. Analyze your own data because this is your discovery. This is your efforts. Third, there are complex and meaningful problems to solve in the life sciences, as you've seen. It's not like everything is solved. Quite the contrary. I really do think the world needs more data scientists like yourselves. And finally, being a data scientist means that you don't need to be a domain expert to make significant contributions in the domain. And so hoping I could have some examples for you, but I didn't have time to go after them. But there are plenty of situations where data scientists actually solved problems that domain scientists have been trying to solve for decades, and they couldn't do it because they weren't thinking big enough. They weren't leveraging the power of this combined brain that I told you about in the beginning in order to help them make that discovery. And so with that said, I'll close it here. And I'll stop sharing my screen and ask you guys if you have any questions you'd like to ask.
Thank you, Helena. It was a very thought-provoking talk, and it was, I think, a very good ending of the whole event. In a sense, I think there are so many things that we all want to think about, but let's see if there is any question for you. It is the end of the day. Okay, so it seems there is nothing here. But there was something, I mean, there were many things in your talk that I personally would like to think about. This is the field that I'm very interested in. But at some point, it seems for you that if we could discover the things that are in the DNA, we could solve all the medical problems in a sense. If the answer is if the question is within the DNA, the answer is also within the DNA. This is something that you feel is correct. So as soon as we discover that, we're going to solve the health issues.
Keep in mind the emergent properties, right? So, and for those who don't know what emergent properties are, think about salt, right? Salt is a very simple molecule, and sodium and chloride, right, together. There's nothing in salt that says it will become a crystal with a certain format, right? Mm-hmm. But you know that if you leave salt for long enough, it will crystallize and the crystals will have a specific shape, right? So that crystal is an emergent property. Biology is full of those, right? So the information in the DNA may not be sufficient to figure out what those emergent properties will be. So you do need to somewhat include the complexity elements that will allow you to encode also for those emergent properties.
Yeah, but if we get to the point that emergent properties are not really random, there's a pattern, there's some mechanism for them to happen that we don't know yet.
That's right. So, yeah. But it's not encoded in the single molecule of salt.
Yeah,
right?
Yeah, that's
it's
true.
encoded in when you have many molecules of salt together. That's when the crystal forms.
Yeah, that's true. Thank you very much. It seems there is no question, but I think you may contact Helena later if you had any questions. And I'm sure there are so many things that you would like to think about. Thank you very much for being here, especially this early in the morning.
No worries.
I really enjoyed your presentation. And now we're getting to the end of the event, and I am not planning to share any screen anymore, but I will just going a few closing remarks, and then we can call it the day. First of all, I want to thank all the speakers who accepted to be part of this event today. This was a very nice set of talks, and there were so many things we discussed. And it seems that we're actually moving toward this smart living in any and every single way. We talked about doing things smarter, and it seems that is the future. And that is where the data science plays a great role, and we are all planning to be part of this wave. Another point, and I also want to thank all the audience to this event. It wouldn't have happened without having you all here. I am very happy to see you join the event and being this late with us. As I already said at the beginning, we have the opening the concept of WiDS Turku clusters, and I would very much appreciate and would love to see so many of you joining that. Together, we may be able to have some impact in the society we are living in through data science, machine learning, and AI. There is a form to be filled in if you're interested. Well, now this is, I'm going to share the link in the description, in the chat box here, and I also will send an email later. Go through the form, see if you're interested to join any of the clusters. You want to propose a new cluster, or if you are interested in receiving occasional emails from WiDS Turku to be informed about the coming, the future events. Our next year event, and I'm hoping to be able to continue this annually. I hope, very much hope, so that it's going to be physical, so we could meet in person. After all, one of the main goals of this event is building the networks of finding people who think like you. So next year, we are planning to hold this event annually here in Turku. We don't know the date exactly. It depends on so many things. And first of all, the pandemic situation. But if there are any women data scientists that you want to hear from, you could nominate the candidates. You could send me emails. You could send WiDS Turku email, and later we will have a form for nominating the candidates. And as I said, there will be some occasional newsletters. So if you're interested, subscribe to fill in this membership form, and then we will get back to you. And by that, I am closing the event here. I hope and I wish a very happy summer to you all. Hope the situation resolves soon so we get back to the normal, we meet in person, and we do great things together. Thank you for being here. Have a nice evening. Bye.
Thank you, Sabina. Bye.
Thank you. Bye.